get the Today is Thursday, May 21st. Today's Thursday, May 21st, and we are going to continue our discussion of descriptive statistics. Before I get started, are there any administrative questions for me? None? Just a couple of reminders then. Have you finished your experimental participation credits? Yes. And if you haven't, you're going to soon, right? Because that has to be done by the last day of instruction. If there aren't any more, or if you don't find studies you want to sign up for, there is a paper option, which is actually a great option. You read an article written by one of our faculty members, and you describe it. So it's very similar to what we've been doing here of describing this research and critiquing the research. So either of those are very good options for expanding and applying your knowledge that you're learning here in this class. There is a worksheet due on Monday, and Monday's a holiday. I know, I'm so sorry. It's just that we've got to get it in before Tuesday, because it's Tuesday we are starting something else, and you've got to have done this worksheet before we go on to the next one. So you'll have all the material for it by today. Get it done tonight, and you don't have to worry about it over the weekend, and you can have a long weekend. Other questions, comments, queries? No? We're good? Okay? All right, well, I wanted to show you some of the data that we gathered on Tuesday. So the data that we gathered on Tuesday was whether you would choose to save 5 innocent bystanders, which meant that you would have to actively kill one innocent bystander, cartoon characters. And what was so that was the outcome variable, was will you save these 5 people? And we measured it on a scale of 1 to 5, with 1 being I definitely wouldn't, and 5 being I definitely would. And so here is the histogram for the 221 of you that answered the question, would you save 5? What is a histogram? What does it show us? What is this telling us? Yeah, Patrick. So it's the distribution. It's how many people said 1, how many people said 2. So this is frequency in the number of people. So 80 people said 4. And about 50 said 5. And so we can see of this group, there's this frequency of these responses. So we're just describing one variable. We're just describing the outcome variable. Does this look like it is a normal distribution? We talked about that ever so slightly on Tuesday. No, why not? In the front row, why are you shaking your head there?
Well, a normal distribution would have most of the participants in the middle.
We would want 3 to be the biggest, and then to be absolutely symmetric around that. And this doesn't look quite symmetric, does it? It looks like more people are clustered over here on the 4 and the 5, and then there are fewer on the 1 and 2 and 3. So we would call that a skewed distribution. So a normal distribution, everything is symmetric around the mean. A skewed distribution has a tail that goes either negatively, it goes lower than the mean, or the tail goes positively, it goes higher than the mean. So in these, you can see there's the normal. If it was symmetrical, it would be like that, but it's not symmetrical. And so this would mean that there are outliers, that there are people, that it's not symmetric around the mean, that there are outliers. This is not normally distributed. Is this the information that you want to see? Does this answer the question you've got about this data that we gathered? No, why not? What's missing? The second variable. So what was the predictor variable? Do you remember? I think we decided to call it proximity. That whether your decision was you were very close to the guy that you had to kill, you had to push him, or whether you had a distant or a far proximity and you were just flipping a lever. So you would like to cut this up and compare those two groups, wouldn't you? And we will get to that. I promise. I'm gonna like draw this out as long as I can because I know you're interested in the answer. So, element of surprise. So this is the whole group, but what we want to do is split this up into the two groups. We measured one other variable that we thought might be a predictor variable. What was the other variable that we measured? It was sort of a morality. Let me show you the distribution for that. So I've called this sort of locus of morality, where one was very external, that as you were growing up there was a higher power who made the rules and was watching you. And then 10 or 9 was you've got to be good because you've got to be true to yourself. It's an internal locus. And so here are the way that you answered those questions. Isn't that interesting? The odd numbers, 1, 3, 5, 7, are far more popular than 2, 4, and 6. I wonder why. Isn't that funny that you went with the odd numbers instead of the even numbers? But this is the whole group of that decision. I decided to correlate those two variables. I had two continuous variables, your locus of morality and your outcome, whether you would save 5. So for across the whole group, and there were 209 of you that answered both of those questions, the correlation came out at 0.03. Do you remember what we know about correlations? Does 0.03 sound like anything that we would get excited about? No, it sounds really close to 0, doesn't it? Do you remember what we want our p-value to be? Less than 0.05. Is our p-value less than 0.05? No, it's nowhere near. So there's no evidence to support that these two are related to each other. And this, again, is the whole group. We can also drill down and look at the two different groups. But this is what you wanted to look at. You wanted to look at the histogram for those who had to push the guy. So there's the histogram for those who had to push the guy. Looking at this, let's see, this is looking much more normally distributed, isn't it? Much more symmetrical. When we look at a distribution, we say a normal distribution is symmetrical around the mean. And what's the mean? What sort of descriptive statistic is it? It's a measure of central tendency. So if you had to guess, where's the mean in this? It's going to be maybe a little bit higher than 3? Yeah? And then we haven't talked about that. So we talked about the measures of central tendency. We haven't talked about the variability yet, but that's how spread out it is. So let's have a look. So the mean was 3.1. The other measures of central tendency, the median and the mode, as you can see, isn't the mode should be 4. This was when I was putting them in the different program. No, this is the same program. I will have to go back and look at that because the mode should definitely be 4 if that histogram is accurate. But there were quite a few people who had answered 1 or 2 or 3, all that I had to delete different people for different parts of the analysis because they said, oh, there's no one in there. Anyways, the mean is 3. We're going to talk about the standard deviation in a few minutes, and that in this case is 1. So here are the descriptive statistics for when you have to push the guy. So when you for the far proximity, you think the mean's going to be higher than 3.1. So let's have a look at that distribution. So here is the decision for when you just had to pull the lever. And what do you think the mean is here? It's got to be around 4, right? Because there's a whole bunch of 4s and 5s and almost no 1s and 2s and 3s. And the mean is 4. And in this case, the mean, the median, and the mode are all 4. So those are the some of those descriptive statistics for that data that we looked at. Okay. So this is a table that is going to tell us which statistics we use when. Our decision on which statistics we used is entirely dependent on how we measured our predictor variable and how we measured our outcome variable, except if we've got categorical and continuous, we then also have to ask, is this normally distributed? Name one of the descriptive statistics that we were just talking about. Mean? So mean, central tendency, mean. Which row do you think mean goes on? Row 1, 2, 3, or 4 there. All of them? So let's think about this. So if we've got categorical predictor variable and categorical outcome variable, we talked about that really early on yesterday, Tuesday, whenever it was. I have no life other than here. When we have categorical predictor variable and categorical outcome variable, all we've got are counts. We've got how many people fall in this cell, how many people fall in that cell. How did we summarize it? Right here. What did we calculate? Percents. So percents are descriptive statistics for which situation? Categorical, we're going to calculate percents. And we're going to do frequencies, we're going to do counts, we're going to do histograms. Because there's nothing to average. In order to average, our outcome variable has got to be continuous. Aha. All right. So moving down, if our outcome is continuous and our predictor variable is categorical, we've got two groups where you in close proximity or in distant proximity, and your outcome is on a scale of 1 to 5. That is when you are calculating the mean for your descriptive statistic, for your measure of central tendency. If your data is normally distributed, if it was skewed, we said that the mean was very heavily influenced by outliers. That one outlier really drags your mean way out there. So what we use an alternative measure of central tendency that isn't as effective, as affected by outliers. And it's the one where you line them all up and you fold them in half and you find out which one is on the crease. Median. We've talked about continuous and continuous as well. We just looked at something about continuous and continuous. When we have two continuous variables, we start by doing a scatter plot. And then what's the other thing that we're doing there? What's the name of the other statistic that we've been talking about, that we just looked at? We had an R equals to 0.03, and we said we're not very happy about it. You see, you've already got that one down. So for our trolley problem data, I also took the liberty of making it into categorical. Do you see what I've done here? Our predictor variable, whether you were close proximity or far proximity, was already categorical. And then I've made our outcome categorical by lumping together the ones and the twos and saying, well, those are all the no's, and then the maybes, and then the yeses. So in order to, it's very hard to look at this raw data. What do we do in order to make that easier to understand? Percents, yep. So we would say of those who were in close proximity, and we would sum that up. We would have the n, and then we'd do 33 divided by n times 100, and we'd do 32 divided by n times 100. And we would do 12 divided by n times 100. And we would have percentages there. And as we looked at with the means, these are looking pretty different groups. It's looking like our predictor does predict. Okay? So, we are talking about descriptive statistics. We have talked about when we have categorical outcome data sets, all we can do is percentages and frequencies and counts. When we have continuous outcome data sets, we need a measure of central tendency, and then we need a measure of variability. We've talked about the measures of central tendency. They all start with the letter M, mean, median, mode. Mean's our favorite. It allows us to do other things, but because it's assuming that they're normally distributed. Let's look at the measures of variability that go with those measures of central tendency. So variability is how spread out is the data, how dispersed is the data. Is it very tightly clustered around the mean, or is it really quite spread out? And we're going to talk about 3 different ways of describing the spread of the data. We're going to talk about the range, the interquartile range, and the standard deviation. The range is a really, really simple measure of variability. It's the highest score minus the lowest score. So in this case, this sample data, what is the range? 8. Yep. So it's a really simple measure. It doesn't give us that much information. It's not that interesting. But it gives, it's just the highest score minus the lowest score. When we report the median, the measure of variability that we report with the median is the interquartile range. So to calculate the median, we lined up all the numbers and we folded the piece of paper in half and we looked at what number was right on that crease, what was the central number. The interquartile range, what we end up doing is taking the top half of that strip of paper and folding it in half and seeing what's on that crease, and taking the bottom half and folding it in half and seeing what's on that crease. So if our data was laid out along was sorted from high to low, if this is the middlemost point, the median, then we find the median of the top half of the data and the median of the bottom half of the data, and we report those two and the range of those two as the measure of variability. Quartile is just a fancy way of saying quarters. So we're going to take the data and split it into 4 quarters and say we've got the minimum, quartile 1, quartile 2, quartile 3, and the maximum. We use this if we have a skewed distribution. So if this is our data, and you can see we've got a skewed distribution because we've got this one funky outlier here. Most of the data is right around, 6, but we've got one outlier at 90. So the mean of this data set is 11.06. So because there is this outlier, the mean is really dragged towards the outlier. And that's why when there is a skewed distribution, when there is an outlier, the mean ceases to be the most useful measure of central tendency. Because that doesn't really tell us what the center of the data set is. The median is 7. Because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 data points. And so this number here, there are 7 below it and 7 above it. That is the median. And that's a much more informative measure of central tendency in this case. So we're going to call that quartile 2 It's in the half. That's 7. So what's quartile 1? We're going to take these 7 numbers and find the median of those. Which one is the median? That first 3, right? So that first 3 is quartile 1. How about quartile 3? Which was the median up here? That first 9. So we've taken our data, we've ranked it, we've folded it in half, and then we folded it in half again. So we've got the first quarter, the second quarter, the third quarter. We've got the minimum, the maximum. Our interquartile range, we say, is quartile 3 minus quartile 1. 9 minus 3 is 6. So we say the data is gathered around the number 7, plus or minus, with an interquartile range of 6 points. So 3 above, 3 below, roughly. That is the middle. What it's telling us is the middle half of the data is between those 2 quarters, the quartile 1 and quartile 3. To display this graphically, we draw what we call a box plot. So here is our scale. There is our median. We then draw a box around the middle half of the data, so quartile 3 and quartile 1. The thing to remember in a box plot, and it's kind of counterintuitive, is that small means important. Small means concentrated. Big means not important. Big means really dispersed. So we've got our quartiles 3, quartile 1, quartile 2, and quartile 3, and then we put the minimum and the maximum. So each one of these blocks represents a quarter of the data. A quarter of the data lives on that line right there. Small means important. A quarter of the data lives on, but in that half of the box, in that part of the box. A quarter of the data is crammed into that part of the box. And then a quarter of the data is spread out all the way out to there. So big means sort of not so important. Big means that it's still a quarter of the data, it's just really spread out. Whereas this tiny little section here means that you've crammed a quarter of the data into that very narrow range. So this is the box plot and how we would display the median and the interquartile range. You can see that it's not symmetric. You can see that it's not normally distributed because the whiskers are not symmetric. The median is not in the center of that box. And that is how we display our, when we have a skewed distribution. Let's write that one in. What does the interquartile range go with? Which row? What does it go with? Row 1, 2, 3, or 4? 2. So we have the median and the interquartile range. Those are our measures. Those are our descriptive statistics. When we calculate the mean, the way we describe the variability is by calculating the standard deviation. This shows how closely those scores are clustered around the mean. It's literally the average, the standard, the average deviation amount that the scores differ from the mean. So we're going to find out how much each score, how far away each score is from the mean, and we're going to average those differences. So when you got the mean, you always report the standard deviation. So these are 4 normal distributions. They all have the same mean, right? They're all right there at 50 with the same mean, but they have very different standard deviations. Which one's got the smallest standard deviation? The really tall, skinny one, right? All of the observations are really tightly clustered right around the mean. Whereas this one has got a huge standard deviation and it's very spread out. So if here are some scores on a quiz, the mean is right there at 5. We want to know what's the distance from each score to the mean. So this person scored a 10. What's the distance? How much does that differ from the mean? It differs by 5. How did you know that? You counted, and what else could you do? Subtract. Okay, we can subtract, right? That's an easy thing. So we're going to take each of those scores and subtract the mean, and we're going to find out how much does each one differ from the mean. And then we're going to average those together. We're going to average those distances. So here are those scores. The mean is 5. We're going to subtract 5 from each score. And here is our score minus the mean. Okay, so what happens if we average that? To average those, the first thing we have to do is add them up. If we add those up, what do we get? Big fat 0, right? Because that's what the mean's in the middle. So there's just as many points above it as there are points below it. So of course the differences away from the mean would be a big fat 0. So we've got to get rid of those negatives. We've got to get just the distance, not whether it's above or below. And I bet you can think of 2 ways of doing that. Absolute value. Oh, it would have been lovely if they'd done the absolute value, because then that would make, I don't know, it would make my life simpler. But those darn statisticians, they decided to square them instead. So we're going to take the score minus the mean and square it. Okay, now we've got all positive numbers. So we're going to average those. First step in averaging them is adding them up. So here's the Greek letter sigma, the sum of the scores minus the mean squared. In this case, it's 58. And this becomes quite an important number. It's called the sum of squares. And we will talk about it again, and you'll say, oh, I remember that had something to do with variability. That had something to do, we got to that number along the way of calculating standard deviation. It has something to do with variability. So we've got our sum of squares. What's the next step in averaging that? We're going to want to divide it by n, aren't we? We're actually going to divide it by n minus 1. And this is we do this in part just to sort of be humble. We don't want to underestimate. We want to, if anything, we want to overestimate. And so this is a way of we ding ourselves if we've got a very small sample size, because we know that there'd be some more chance of random noise or random error in a small sample size. So dividing a number by 7 versus dividing a number by 6 is really quite a big difference. If we had a big sample size, dividing a number by 101 and dividing a number by 100, really there's not much of a difference there. It becomes a much less of a difference. So we're dividing the sum of squares by n minus 1. And we get 9.67. Are we done? Is that our standard deviation? It seems awfully big, doesn't it? Because the mean's like 5. It doesn't have a standard deviation of 9. What do we have to do? We have to unsquare it. Right, we squared it, so now we have to unsquare it. We're going to take the square root of that, and we end up with the number 3.11. That is our standard deviation of this data set. So this data has a, whatever it was, a mean of 5 and a standard deviation of 3.11. Okay, I'm going to show you the formula. Take a deep breath. The anxiety will pass. Okay? Yeah, this is exactly what we just did. So take each score minus the mean, square that, add all of those up, divide by n minus 1, and then take the square root of it. There are other formulas. There are other formulas for standard deviation. There are some calculation formulas. They all pretty much get to roughly the same place. This is the formula that we're going to use. You are being asked to calculate standard deviation on your homeworks. You will be asked to calculate standard deviation on the exam. It's just to demonstrate that it's not that scary a concept. We're going to use small groups like 5, 6, 10, 12, small groups. And from now on, I'm sure that you'll have a graphing calculator or you'll have a computer program that calculates this for you. But to really own this concept that you've got the average and then you've got the average distance from the average. and that's really a pretty easy concept to demonstrate. So there are a few times that you're being asked to do that on your homework. Also, so for midterm 3, there will be some calculations. You'll be calculating average and standard deviation. I will give you those formulas on the exam, and you're welcome to bring a simple calculator, not a graphing calculator, but a simple calculator. One that does square root, but not that one that you enter the data and it tells you everything for you. Because these aren't that hard concepts, and I really, when we get into the discussing the conclusions that we draw, I think that you having ownership of these formulas helps you feel more confident about drawing those conclusions. All right. So where does standard deviation go? Where does standard deviation? That it goes on the third one. Yes, it goes with the mean and the standard deviation. So that's how we describe those sets. So here is your data. Let's calculate the standard deviation for morality. So first off, we need to know the mean. So I'm going to have Excel calculate the mean for me. And I'm selecting all of the data, everyone who answered that question. So the average is 6.111339. So what's the first step? We take the score and we subtract the mean, right? So that's for the first participant, that is their score minus the mean. I'm going to have Excel fill that formula for everybody. Do you love Excel? Do you use Excel? Excel's awesome. Fill that for everybody. All right, so there's all of our distances from the mean. If we added these up, we'd expect a 0. So what did we do? We squared them, right? That times themselves. So I've said take this equals, in Excel, you write a sentence to get Excel to do something. In English, a sentence starts with a capital letter. In Excel, a sentence starts with an equal sign. And then you refer to the cells with their letter and number. So equals this times itself. And we're going to fill all of those. Oh. Do you see what I've got? All the people that didn't answer it are messing up the data. I want to clear those. Those are not part of the data. All right, so there are the ones that are part of the data. If we so if we add up these, what did we expect this column to add up to? Oh. Equals sum from D2 to D2 10. What have I done? Oh. Thank you. So that adds up to pretty much 0, as we expected. And when we add up the column that we just squared, what is this number? So that's the sum of squares. And all you need to do is remember that the sum of squares was a part halfway along towards calculating the standard deviation. It's got something to do with the spread. What other piece of information do we need? N. How many were in the group? How many answered that question? $209. Now what do we want to do? Let's do it in little steps. So equals that divided by 209 minus 1. Oh no, so that's the formula is the sum of squares divided by n minus 1. All right? Yeah? And then what was the last step? And so we think that our standard deviation is 2.203. Shall we see if Excel agrees with us? Because Excel will do that all for you. Oh. Boy, I am. We want the standard deviation of the morality. That's what we want the standard deviation of. Those 1 to 9s. What do you think it's going to be? All right, so Excel agrees with us that the standard deviation, so that's the formula that Excel is using. You can now do that. It's pretty simple, right? No, that wasn't what I wanted. All right. So we took each score, we subtracted the mean, we squared those, we added them up, we divided by n minus 1, and we took the square root, and that's the standard deviation. Clickers, 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 where are your clickers? All right, I'm seeing most of you there, or a bunch of you there, and 98% of you have proven that you know that you calculate a mean if you've measured your outcome continuously. In order to average something, it's going to have to be along a continuum. It's going to have to be numbers, not groups. When are we stuck with a frequency distribution? Why, yes. You're right, it's the other answer. We can also do a frequency distribution for continuous, but for the most part, we think about those for categorical variables. We've talked about 2 categories of descriptive statistics. One of those categories was central tendency. Three of those are a measure of central tendency, and one of those is not a measure of central tendency. The measures of central tendency all start with the same letter. Ah, there you go. So what is the other category of descriptive statistics that we talked about? We talked about measures of central tendency. We talked about variability, and standard deviation is a measure of variability, while mean, median, mode are measures of central tendency. When you've got a mean, how do you talk about the variability? All right. Mean goes with standard deviation. What goes with interquartile range? Median. Do you see the red and the blue one? So the blue is the really skinny one and the red is this one. So the red and the blue are right there still on that same, they're centered at the same place, their central tendency is the same place. The difference is how spread out they are. So which one of those is how spread out they are? All right, I've got 95% of you correct on that. The standard deviation is the measure of variability or spread. That is how spread out those distributions are. The central tendency is where they are located. So the blue one and the green one differ on their, well, both really, isn't it? But the green one's different from the other three, from its central tendency. Its mean is way down there. But those three that are on top of each other, they are mostly differing in their measure of variability. All right, so we have discussed these descriptive statistics. Yes? Questions about those before we move on? You feeling pretty confident about them? All right. I want to talk about another very related concept, and that's the concept of standardized scores. Just make sure I made all my notes. Yes. So we've talked a bunch about that we make up scales all the time. We make up introversion, extroversion scales, or we make up a scale of how much your sweetie pie loves you, or we make up a scale of how intelligent you are. And in the social sciences, we are constantly making up these really arbitrary scales. And that becomes very difficult to compare or to understand what that means. So here's one that we've talked about before. The personality self-report on extroversion, introversion. Yes, you remember talking about this one, right? Where we've got, we're asking people to answer most of the time, often, sometimes, rarely, almost never, to these. When I go out socially, it's usually with a large group of friends. So if we wanted to know the most extroverted person in the world, is that better? It seems like you'll be able to see the screen better. So the most extroverted person in the world, how are they answering this first question? That give them the most of the time. I go out with a large group of friends. I work out my problems on my own. The most extroverted person would give that a 5. I plan what I'm going to say. Never. I eagerly share always. I'm very talkative, always. And so we would reverse the scoring on those questions, those two questions, so that this person has scored a total of 25. And the most introverted person would give us the opposite pattern of results. We would score it in the same way, so they'd be on the opposite end of all of those scales, and their total score would be. And we would expect those to range, so they'd range from 5 to 25, and we'd expect them to be roughly normally distributed. Many of the characteristics that we're interested in, turns out they are normally distributed in the population. So there would be a few people who were so introverted that they were exhausted by being in groups, and a few people who were so extroverted that they're, I think the people on either extreme of this would be kind of loopy. Most people would be somewhere in the middle. Somewhere right around the middle would be the most common. We'd find our mean right around the middle there. We've looked at this as well. This is a scale of assessing autism. So it's just a screening of, do you think your child might be at risk for spectrum disorders? Spectrum disorders are difficulty with socializing, difficulty with communicating, so eye contact and socializing and fantasy play. So let's give a 1 to the answer that would be, this is a person that this is a child that we'd want to take a closer look at. We talked about this when we talked about surveys, where obviously the best way to determine if a child is at risk for autistic spectrum disorder would be to do a clinical interview and assess them. But there are a whole bunch of children, and we could easily, quickly screen and eliminate 95% and just focus on the few that are maybe more at risk. So if you point, does your child look at it? A child who's high on the spectrum disorder, their parent would answer no. Have you wondered if they might be deaf? Yes. Do they pretend or make believe? No imagination, no imaginative play like that. Do they climb on things? And I think we talked about this, that this is probably not even, it was just sort of a distractor in there just to make sure, to kind of put you at ease, that it's like, my kid's normal on this. How many fingers did you have? 10. My kid's normal on that. That this has nothing to do with being on the spectrum. It was just a way of making sure that they are answering or reading each of the questions and not just getting down on the kid. Finger movements and wiggling near their eyes would be a yes. Point and ask for something, no. Point to show you something, no. Interested in other children, no. So in this case, the most likely to have autism, the parent would have answered this 1, 2, 3, 4, 5, 6, 7. Now, autism is pretty rare. I mean, the prevalence is increasing, but it's still about 1 in 68 children, so it's about 1.5% of the population, which means that 67 out of 68 children do not have autism. So the distribution that we would expect to see for that screening is not normally distributed. It would be skewed. So we'd expect it to be a skewed distribution where most children score very low on that screening, but then there are a few outliers. So that 7 would have been above the threshold where we would want to look at them more closely. So there's 2 pretty arbitrary screening tools or surveys that we've made up where, if I say you're a 15 on the introversion-extroversion scale, it doesn't necessarily mean much. You don't know what that means. If I say you are a 7 on that autism screening, that in itself doesn't give you enough information. So we have these arbitrary numbers that we've ended up with. Let's go back to the standard normal distribution. So we've said that the standard normal distribution is symmetric around the mean. It actually, when we say that something is normally distributed, we are talking statistical secret code. We are giving a huge amount of information. So we're saying that the scores are symmetric around the mean. But we've also quantifying how by using the mean and the standard deviation, we are communicating a very specific relationship between the mean and the standard deviation. So when we look at the normal distribution, we look at if we go one standard deviation above the mean, so the mean plus one standard deviation and the mean minus one standard deviation. And it turns out that in every standard normal distribution, 68% of the observations are within plus or minus one standard deviation of the mean. So the standard deviation or normal distribution gives us a huge amount of information, and these specific percentages are what it implies. If we go out another standard deviation, so the mean plus and minus 2 standard deviations, that covers 95% of the population. If we go out 3 standard deviations, that covers 99%, more than 99% of the population. So it's very usual to be within 1 standard deviation of the mean. It becomes pretty unusual to be more than 2 standard deviations above or below the mean. And it's downright rare to be more than 3 standard deviations above or below the mean. Let's practice that. So if I was to tell you that the that men and women, these are the mean and standard deviation heights. So women have a mean of 5'5" with a standard deviation of 3.5 inches. Men have a mean of 5'10" with a standard deviation of 4 inches. What does that tell us? What do we know? Let's start with the men. So we're going to want 5'10" right there. What's plus 4 inches? What's plus 1 standard deviation? It's hard because it's feet in inches. 6'2". What's minus? What's plus 2? What's minus 2? What's plus 3? What's minus 3? So for the guys, we would expect our distribution to look like that, where it's really normal to be between 5'6" and 6'2". 68% of the population falls between 5'6" and 6'2". It's really unusual for a guy to be shorter than 5'2" or taller than 6'6", and it's incredibly rare to be above 6'10" or below 4'10". That's what the mean and the standard deviation mean. That's what it tells us. Where does the distribution for the women lie? Let's see, their mean is at 5'5". So their mean is 5'5". Plus 1 standard deviation, 5'8.5". Minus 1 standard deviation, 5'1.5". Plus 2 standard deviations, 6 foot. Let's do plus 3, 6 for 3.5. Minus 2, that was 5, 1.5, so it's 410, isn't it? And minus 3 is and so their distribution, I've made that much taller and skinnier, but it's a slightly smaller standard deviation. And again, we would see 68%. We would expect 68% to fall within plus or minus 1 standard deviation. Let's do those. We said that 68% fall within plus or minus 1 standard deviation. Here's the mean. Now let me do it in black. All right. How many are above the mean? 50%, right? It's symmetrical. I really recommend that you sketch this bit out. So 68% are in here. So how many are in this half? Do you see what we did? We just divided that in half. This next one was what? 95%. Okay, so we've got, we've already taken care of the 68. So we need 95 minus 68, which is 27 maybe? And then we need half of the 27 in this section. And then what was this next one? We're going to say 99%. It's actually more than 99%. But for this class, let's just say 99%. So, that's easy. 99 minus 95 is 4. So there's 2% here and 2% here. And then what's left over? What's under these tails? So there was, if 99 is under the curve, there's 1% left over, 0.5% on either side. So let's put this into practice. Let's say I've developed a couple of different tests or scales that measure how much your sweetie pie loves you. We went with the people back to back, right? So if I say, hey, 17, your score is 17. Are you happy? No, it means 17. And she's like, I don't know if I'm happy or sad. What does 17 mean? 17 is arbitrary, right? What do you want to know? Out of what? So, what if it was on a scale of 0 to 26? Are you happy? No? Because you're not near 26? You're not near the top? But what else do you need to know? What's the average? How about if the average is 18? Because you're below the average. But how far below the average are you? Are you normal or are you like rare? You don't know yet. So what if the standard deviation is 0.3? So the mean is 18 and the standard deviation is 0.3. So a score of 17 makes you what? Like you're finding a new sweetie pie tonight, right? But if I said the standard deviation is 3, then like, yeah, okay. So do you see how you're doing that? Do you see how you're thinking about that? So let's play with some of those ideas. So if here are the two tests that I created. All right, we've got test A and test B. You got to sketch them out. You know this now, right? Graphs are your friend. Sketching things out is your friend. So let's see. Let's put this on sort of this sort of scale. Test A has a mean of 18. Mean plus 1 standard deviation is mean plus 2 standard deviations is mean plus 3 standard deviations is mean minus 1 standard deviation is minus 2, minus 3, so we've got a distribution something like that. The other one has a mean of 25, standard deviation of 3, so plus 1 is 28, plus 2 is, plus 3 is, minus 1 is, yeah, it's right there, 22, isn't it? Minus 2 is, minus 3 is, all right, so we've got our two, yeah, it should be taller, our two distributions. Okay. So, you know what? Let's go ahead and write a standard equation of what we've got here. So, thinking about the red scores here, we said 22 equals, how do we figure that out? We said 18 plus 1 times 4, right? And then we said 26 equals the mean plus 2 times 4. Yeah? And we said, that's what we were doing, right? We said 30 equals the mean plus 3 times 4. Yeah? So, what's the 4? The standard deviation. What's the 18? The mean. What's the 22, 26, 30? It's the score, so let's just use x. So the score equals the mean plus some variable times the standard deviation. I'm just going to use the letter z to stand for this variable. So 1 standard deviation, 2 standard deviations, 3 standard deviations. So let me just write that out. We've got x, the score equals the mean plus z standard deviations. So if you had, oh, that's what I told you. I said you've got a score of 17 on test A. Are you happy? You said not really because I'm below the mean. So 17 equals, well, how far below the mean are you? Let's use that formula to figure out how far below the mean are you with a score of 17. You're not that far below the mean, are you? You're not a whole standard deviation below the mean. You're just a little bit below the mean. Time for 7th grade algebra. With you so far? So in this case, z equals negative quarter, negative 0.25. Is that how far below the mean you would be at 17? Yeah. You're a quarter of a standard deviation below the mean. Is that usual? Yeah, that's within that 68%, pretty usual, pretty comfortable. You're not gonna, you're not gonna buy your sweetie pie any chocolates this weekend, but you're not gonna dump them either. How about if you had a score of 17 on test B? How do you feel about that? Just off the top of your head, how do you feel about that? You're not happy, are you? Because the mean is 25 and the standard deviation is 3. Where's 17? Oh my goodness, it's nearly 3 standard deviations below the mean. Let's find out exactly how many standard deviations it is below the mean. So let's use this formula again. So x equals the mean plus z standard deviations. So 17 equals 25 plus z times 3. Subtract 25. We knew we were below the mean. We know we're going to be a negative number here. Negative 8 equals z times 3. Divide by 3. In this case, z equals negative 8/3, which is negative 2 and 2/3. Yeah, you're absolutely right. You're nearly 3 standard deviations below the mean. That's unusual. That's getting close to downright rare. So in that case, you'd definitely be looking for a new sweetie pie. If your sweetie pie's got a score of 34 on test B, what's the equivalent on test A? So on test B is the blue one. So a 34 is like way out here. We think are we predicting, what are we predicting? We're predicting like 30. Let's prove it to ourselves. So we're going to use that same, the score equals the mean plus z standard deviations. I'm just going to do what we were doing here. So the score minus the mean equals z standard deviations. So the score minus the mean divided by the standard deviation equals z. Did I do that right? Okay. So now let's see. We've got 34 on test B. We want to know what z, if we have 34 equals, the mean of test B is 25 plus z times 3. Oh, no, wait, I want to put it into this one because this one's easy. So z equals 34 minus 25 divided by 3. 34 minus 25 divided by 3. So we're looking for a z of 3. And so now we're going to solve for the score in with the mean and standard deviation of test A. So if we said z3 equals what score minus 18 divided by 4 times both sides by 4, we get 12 equals x minus 18. Add 18 to both sides, 30 equals x. You're absolutely right. By looking at this, you said, well, that's 3 standard deviations above the mean. I need to be 3 standard deviations above the mean here too. Do you see what we're doing and how we are doing it? What we are doing is playing with standardized scores. Let me fess up. I didn't just pull the letter Z out of thin air. That is the name of this. They are Z-scores. So a Z-score is, we can convert any scale to this standardized scale. that is in units of the standard deviation. It tells us how far away the score is from the mean in the terms of standard deviation. It's 1 standard deviation above the mean. It's 1 standard deviation below the mean. It's 3 standard deviations above the mean. It's 2 2/3 standard deviations below the mean. The z-scores turn out that they have a mean of 0 and a standard deviation of 1. And so they're giving us that how far away a score is from the mean in terms of the standard deviation. And because we know that it's normally distributed, that tells us how unusual something is. So we're making all of these weird constructs that can't be directly measured. And we've invented really clever ways of estimating those constructs. And often it's just arbitrary. And knowing that your sweetie pie gave you a 17 tells you nothing, or doesn't give you enough information. So converting it to standardized scores, we can easily compare across different tests and easily identify whether we're happy, whether we're normal, whether it's usual, whether it's outside the mean. Let's look at some examples of both standardized tests and other just ways that the studies that we've been looking at, the ways that they have presented their descriptive statistics. So going back to one of the first examples we looked at, when less is more, with the bronze medalists and the silver medalists and the ratings of ecstasy to agony, yes, and what might have been. So here is how they presented their data. What are they graphing here? What's this number? The mean, right? The mean of the silver group at immediate and the mean of the bronze group at immediate, and then a mean of the silver group when they're on the medal podium and the mean of the bronze group when they're on the medal podium. Does it look like, do you predict that, so squint your eyes a little bit and average everyone who is in the bronze group and average everyone who is in the silver group. Do you think there's a main effect of winning silver and winning bronze? If you squint your eyes, does it look like the average of these is taller than the average of these? Yeah. So you'd predict that in general the bronze winners were rated happier. Does it look like there's an effect of time that when looked immediately, if you squint your eyes and average these, and if you squint your eyes and average these, does it look like that maybe goes down a little bit over time? Yeah, maybe a little bit down. Everyone calms down a little bit. So when we're looking at this is actually a factorial design, isn't it? It's got 2 predictor variables. There's, we also are going to squint our eyes and see if we can see an interaction. So if we look at the line that connects those two, how much the silver medalists calm down and how much the bronze medalists calm down, do they look roughly parallel? Yeah, so you're going to predict that there's a main effect of medal type, that there's a main effect of time, but that there's no interaction. Let's see how they presented their results. So they said, when assessing the athletes' immediate reactions, participants assigned the bronze medalists a mean happiness rating of 7.1, standard deviation 2. But the silver medalists a mean rating of only 4.8, standard deviation of 1.9. So they're telling you about that main effect of there's a difference between those two. When examining the athletes on the medal stand, participants assigned the bronze medalist a mean rating of 5.7 and silver medalists a mean rating of only 4.3. So they're giving you the means and the standard deviations. They are being very, very, very precise about how they just define their variables. So they're not saying the silver medalists were this happier. They're saying our participants assigned these medalists this rating. Because remember, it was we just looked at the tape and assigned them a happiness rating. So they're being very precise about describing their outcome variable there. These data were analyzed with a 2 type of medal, bronze versus silver, by 2 tape, immediate versus medal stand, analysis of variance, ANOVA, don't worry about it, we'll get to it next week. This analysis revealed 2 significant main effects, but no interaction. You guys understood that. You guys predicted that. The main effect, oh, this one kind of drives me nuts. So they called one of their variables tape, immediate versus medal stand. It seems kind of sloppy that in their usage they were using, which tape is it on? I mean, you can almost imagine it was the videotapes it was on. Is it on the immediate tape or on the medal stand? But I'm surprised that the editor didn't catch it. A much better name for that variable would be time, or the immediate versus medal stand. It's not so much the tape. But so the main effect of tape, don't worry about it, we'll get to it next week, indicates that the athletes on the whole looked happier immediately after their performances than when they were on the medal stand. So they were happier immediately than later. The main effect of medal indicates that athletes who finished third look significantly happier than those who finished second. So they're being very precise about, I've got 3 more minutes, guys. They're very precise about how they're describing their variables there. The self-esteem and love. This is the sit back to back and write out everything that pisses you off about your partner or everything in your dorm room. And then the results were how attractive is your partner. Do you see that they've got this on the scale of 0? What have they done here? What are they have standardized these scores. They have converted these into z-scores before graphing the means. So let's just have a quick squint look. If we looked at everyone who was in the control condition versus everyone who was in the experimental condition, if we average those in our heads, in our eyes, does it look like that's a difference? Yes. If we looked at everyone in the higher self-esteem group and everyone in the low self-esteem group, does it look like that would be a difference? Yeah. Does it look like there's an interaction? Do these lines look parallel? That line and that line? No. So we expect that there's an interaction and 2 main effects. So they say it revealed a significant main effect for condition, a significant main effect for self-esteem, and a significant interaction. So you're absolutely right that there was all 3 of those. And we're looking at those p less than 0.05s. We're going to talk about the way that they've calculated those that next week. Okay. All right. All right. Have a great long weekend. I will see you on Tuesday.